Hello everybody. Welcome back. This is video number 32 in a series of 35. Each video corresponds with the problem from an AP Physics C Mechanics multiple choice test. This question is the second in a series corresponding to this situation. I'm going to read the situation, the problem, and then we're going to jump into solving it, the physics concepts that you need to know to solve it. Alright. A particle of mass m moves counterclockwise around a horizontal circle of radius r. The angular speed of the particle is given as a function of time t by this equation, where b is a positive constant and t is greater than or equal to 0. So problem 32 asks us, what is the magnitude of the angular momentum of the particle about the center of the circle as a function of time? The answers we are given to choose from are A, mbt all over r, b, mbrt, c, mbr squared t, d, mb squared rt squared, and finally e, mb squared r squared t squared. So let's start with the conceptual aspect of this problem. We're looking for the magnitude of the angular momentum. Angular momentum can be represented as L. It is, let me check the useful equations sheet to see if there's some equations we can use here. Yes, it does tell us that it is equal to the cross product of momentum and radius, and also equal to I omega. So in this case, we are actually given an equation for omega, so that's going to be something that we're going to want to use because we already have that part of it. We don't have the normal momentum, and we do have the radius, but let's stick with this part for now. So another concept at play here is moment of inertia, which is essentially which is essentially the rotational corresponding variable to mass. So I is equal to some coefficient times, let's talk about this. Different objects have different moments of inertia. So in this case, it's a particle. A particle is a point mass, and point masses have inertia of mr squared. So, for example, a disk is going to have a moment of inertia of 1/2 mr squared. Like a full sphere is going to have a different moment of inertia. A human holding out dumbbells is going to have a different amount of inertia versus even when they bring their arms in. That's all going to change the moment of inertia. If you want to learn more about moment of inertia, in another video, I talk about the parallel axis theorem, which is a way of calculating moments of inertia when the point of rotation, the axis of rotation, is changing. So you're going to want to check out that video. I can't remember off the top of my head what problem it is, but you should go back and watch all of them anyways to help you prepare for the test. So this is our moment of inertia for a point mass, which is what we have here since it is defined as a particle. And then for omega, this variable, we're actually given an equation for it. So omega as a function of time is equal to bt. So here, we're not going to use this. You can cross this out. We're going to plug these in. So angular momentum is equal to IW. So I is equal to mr squared, and W is equal to bt. Now let's see if what we have discovered looks familiar in any of these answers. So mbt over r, nope, r should be in the numerator. mbrt, nope, that just has an r, no r squared. By the way, I wrote r capitalized here. That's because that's the way it's usually written in that formula, but it's the same as lowercase r for the radius. They both mean radius. It's the same thing. Here we have mbr squared t, mbr squared t. Yep, that looks right. Let's read the rest just to make sure we have no overlap. mb squared rt squared, nope, there's just a b. No b squared, and then a whole bunch of squares, which is wrong. So, yes, C is our correct answer. So, quick recap. To solve this problem, we used the equation angular momentum is equal to IW, moment of inertia times rotational velocity. Moment of inertia for a point mass is mr squared, and we took the equation for angular velocity from up here. It is equal to b squared. We plugged each of these into the equation, and that's it. That's our answer. Thank you for watching. Let me know if you have any questions, comments, suggestions, concerns about this video. And we're on 32, so almost done. 3 more videos to go. Thanks for watching.